incoming, this is all the energy. 1/3 of it goes to the electron. Okay, so it gives it 10 keV. It keeps 2/3 of the energy. So when it scatters, it still has 20 keV. Right, that's all that's going on here. Yes, Cody. Well, okay, now, once again, this isn't entirely accurate, right, because this does also lose a little bit of energy due to the binding energy.
Okay, so that, but this one is a.
Where is that? What do we need to know for that?
What is that?
Do we need to know how to do that?
So generally speaking, I want you to know this overall interaction, right? It loses about 1/3 of its energy, so the scatter photon still keeps most of its energy. Right? This is the main thing here. It keeps most of the energy when it scatters. So the scatter is high energy, relatively speaking. Right? Because the scatter is high energy, it can travel through the patient and reach our IR as remnant radiation. Right? It goes through the patient, exits the patient, remnant radiation hits the IR. Or exits the patient, goes away from the IR, so just regular scatter, it's not remnant, and hits us, occupational dose. Right? That is why it's important to know this is relatively high energy.
And this concept of radio, what is it called?
This is Compton scatter.
And no matter what the 30 keV says, it can be 60, 70, still applying the same rules. 2/3 goes to Compton and 1/3 goes to the other part, electron.
Is the reason why it's called a secondary electron is because not all of the energy is absorbed? Because the other one's called a photo electron, but this one's called secondary.
I don't know where they came up with these names, to be honest.
Okay, we just need to know the difference.
I think it's also called Compton.
Compton electron.
Yeah.
There's a lot of different names for them.
So
This is still the third one?
we get this one.
So this is the third, and
So this is the fourth and final one. So which interaction produces an ejected electron and a lower energy scatter photon? Yeah, that's the one we just did, okay? And then how much is Compton? How much energy is it taking?
It's gonna give the electrons in the third and keep to that.
Say that one more time.
The electrons gonna have 1/3 of the energy and the photons gonna have
The Compton, yeah, okay, sounds right.
Okay, one more time, Charles.
two.
So I'll
The
make sure.
electron is gonna have 1/3 of the energy and the photon, the secondary one, is gonna have 2/3.
Compton
Thank you.
goes with 2/3. You can know what Compton is 2/3, you can solve what the other one is.
Are there other names for Compton?
Compton scatter.
Incoherent?
I don't think I've seen incoherent used for Compton scatter.
Is it incoherent something else?
Isn't it the?
Because I thought that on the slide it said,
So there was inelastic. Oh, actually, yeah, we do have incoherent. No, you're correct. We do have incoherent. We have modified Compton. I think that's it. I think there's 4 names for it.
there was a name
modified.
like we have Rayleigh and Thompson. There was one for Compton.
It was not Thompson, it was just the incoherent, inelastic, and.
No, I was saying like we have for classical. There's Rayleigh and Thompson. Compton has one too, I think. I don't remember the name.
Yeah.
Can you? Yeah,
We good? Any questions?
I think it's the slide before.
The 4 one?
No,
So the second ones that we're about to do are a lot more simpler, and these will not occur in diagnostic imaging, okay? Because these two are measured in MEVs instead of KEVs. And MEVs is it higher or lower than KEVs? Higher, way higher, and these won't be seen in diagnostic imaging, correct? So everybody got their pen and paper out for this? Nope. I hope you're ready.
Real quick, what is a KEV? What is an MEV? All right, kilo, what does that mean?
1,000.
1,000. Mega, what does that mean?
1,000 of mega is 1,000 of 1,000.
Mega.
That's right, it's a million. So we are setting millions of electron volts here.
That's a lot.
It's a lot.
It's too much. Bruce Brown. Alright, so pair production, this is very simple. It's in the name. So key phrase right here, requires a minimum of 1.022 MeV photons. So that'll be a test question. It will ask how much energy is needed to produce this interaction. And that interaction will be 1.022 MeVs, keyword MeVs. Because you might put keV, MeV, some other number, you gotta know it's MeV, okay?
1.02.
One point-
This is the same thing.
Yeah, 1.022.
Okay, I think before we said that.
So in the book, I think this book just says 1.02.
Yeah.
If you want to be more precise, it's 1.022. So you're close enough. I'm not gonna do something like 1.01, 1.02, 1.03.
You should.
You know what?
Maybe for the seniors.
Maybe I'll change the test questions.
He said maybe for the single.
He's the one that goes to the zoo.
I can bring some popcorn back.
I don't think he would make it because he.
All right, so let's focus. Let's focus. We do need to quickly get through this.
So let's hurry up. So like I said, since it's measured in MeVs, this will not be found in diagnostic imaging. So if you see MeVs, you already know that it's not part of diagnostic imaging. And so the interaction between the photon and the nuclear electric field. So this is very key important because no other interaction that we have went over through is part of the nuclear electric field, okay? So that's very important. So as you can see, the reason why I like to call this pair production because it creates a pair of
Pair of particles.
pair particles, correct? So you see the incident photon, it interacts with the nuclear electric field. Do you know what the nuclear electric field, when it explains that? Okay. So it's not hitting the nucleus, it's not hitting an orbital. It's hitting like the little space. You see this little space that we have right here?
It's passing by the
Yeah, it's passing by the nucleus. It's not hitting an orbital, it's not hitting an electron, it's not hitting the nucleus. It's hitting the space right around the nucleus. Everybody get what I'm saying? Like, you see this little space right here? Yeah, so that's what it's hitting, okay?
It's the space between the nucleus and the orbit.
Yeah, exactly. Perfect. And so when it creates that, it creates this pair production. So this is like a zoomed in part right here. As you can see, when it hits the nuclear space, it hits this and it creates two resulting photons. Not yet? No. That just okay, that's too far. Okay. Okay, so when this interaction happens, it creates the photon is absorbed and it converted to matter, okay? So another test question, it can be said, which interaction creates matter? And you would know that it's pair production, all right? And the results that are produced are these two right here. An electron also can be known as a negatron, okay? And the other thing that can be produced is a positron. A positron, highlight this, positron is a positively charged electron, okay? So what is a positron again?
Positively charged electron.
Positively charged electron. That will be on your test, I promise you. I've seen that every semester, okay?
So just think of this as like twins, right? Except one's the good twin, one's the evil twin, right? So you're creating pairs, right? Creating twins, but one is positive, your positron, and one is negative, your negatron, your electron.
And you guys seen Transformer, right? You know you got that guy, what's his name? Megatron. So think of it, Megatron evil and Negatron, right? That helps? That helps? That's how I thought of it.
So negatron is called an electron also.
Yeah, and that's the negative one, right?
Oh. So rather electron.
Yes. And if it's, and this might be another test question, it might be, what is the equation of matter? It'd be energy equals mass, correct?
Mass?
MC squared.
Times,
C, yes, what is C? Great question. So
C is the
Einstein's
speed of-
famous equation, right?
The speed of light.
Yeah.
Yes, C is the speed of light.
squared.
So Einstein became famous because he was the one that proposed that energy and matter are actually connected, right? That energy is equal to mass times the speed of light squared, which means that you can actually convert energy into matter and matter into energy. You can actually go back and forth between the two. So in this case, what is a photon?
A positively charged.
No, photons have no charge. What is a photon?
Is it energy,
Energy.
or mass?
Energy.
It is a packet of energy. Good. So energy comes in, and what comes out?
Matter.
Matter. We went from energy into matter through Einstein's equation.
That's just for this, that's just for.
Only for pair production.
Any for prepared.
Only pair production has enough energy to create matter. If you don't have enough energy, you cannot create matter here. So the energy needs to be high enough. How much energy?
1.02 mega.
Good. At least 1.02 mega electron volts. Yes, John.
So we don't use MEV in diagnostic radiology.
Correct.
So where do we
This
use
is
it?
to KEVs.
So, where do you see MEV? You will see MEV in places like nuclear medicine,
So PET scan.
PET scan,
Um,
or radiation therapy.
Have you guys seen the machines and radiation therapies or not? Well, I think when you get a next semester, you guys can have a rotation through there.
Not yet. Or next year, next fall.
Next year. Oh, next fall. Okay, next fall. And you will see the machines. They're 10 times bigger than you would see in CT, MRI, or even X-ray. Because these machines take up the whole room. That's just how much energy it produces.
Yes, Jay.
so is the negatron a neutron that's been negative?
No, negatron is literally your normal electron.
Yeah, it's just different name.
But
Right.
there, I
And
thought
that-
there weren't any.
So these electrons here, this electron, they're literally the same thing. It's just this one was created out of energy.
Oh,
These
so
electrons
it,
were
didn't, it
already
didn't exist before. Like it
Correct.
was- okay.
At all. So this is an electron that pretty much came out of thin air, right? Created matter out of nothing. But it's not nothing, is it? We created matter out of what?
Energy.
Energy.
Energy, good. So energy created this electron. Energy also created this positron. We always create both, which is why it's called
Pair production.
good. Right?
So calling negatron electron would be wrong.
They're the same. It does
But we
come.
can, that negatron can also be called an electron.
They are the same, yes. Just like you can be called Shaheen or you can be called Miss Parak, right? Same thing.
So let's get this clear, okay, guys? So what we have, 1.022 MeV is the nuclear field, which produces two things. These two things are these two, okay? So it's basically energy converted to mass, which create these two. These matter, okay?
This is the mass that's created.
This is the matter that is creating.
Matter as mass.
So these two, okay? Anybody have further questions on this? We're all good? All right, on to the next. So electrons end up captured by neighboring atoms. So what it's saying, whenever this gets shot out, this is somewhat and sometimes gonna hit another atom to create another interaction. Depending where it hits, it can be any of the three. It can be classical, for pair production, or Compton. Any of those three, correct?
So not quite, because remember, for those interactions, what needs to be incoming?
Incident photon.
Photon. Right, so this instead could actually cause, yes, it's an electron, right? What kind of interactions can an electron cause? Browns or characteristic, right? So you could actually get those inside the body with a high enough energy electron.
Wait, I thought those were only inside the tube.
Yes, so that's why, right? Not part of diagnostic. Don't worry about that too much, right?
Just worry about it.
Don't worry about that too much. For our purposes, Brams and characteristic is tube only, right? For our purposes, right? In reality, things are a little bit messier. That's okay. I'm gonna hide the mess from you, right? So don't worry too much about what's gonna happen afterward. Just know that this ends up going to another atom. The atom might grab it, turn it into its own electron, or it might cause something to happen. But don't worry about the something, right? The electron just ends up being absorbed into the body sometime down the line. But the electron stays. That's the key point. This electron stays. It is now a permanent part of the body. But what about that positron? What happens to the positron when it leaves the atom? Yeah, so the positron is antimatter, right? You may have heard about antimatter in science fiction. No, antimatter is real. It is an unnatural particle. It does not normally exist by itself. So, if it does interact with another electron, if the positron is floating along and it runs into an electron, so positron is what charge? Positive. Electron is what charge? Positron is what kind of matter? Antimatter. Electron is what kind of matter? Normal, right? Regular matter. So when they run into each other, right? It's
collide.
like the good twin and the evil twin meeting up, right? And then they have this giant battle between themselves, right? Yeah, they got beef, right? So, right? Right? 3-movie trilogy, right? Of them just battling each other. And so when they fight, right? And then at the end of the series, they're both like dying, right? And you're like, well, I hated you all my life. I'm like, yeah, same tune, right? And didn't they both die? And it's like a sad ending.
I was just thinking.
Right? So they both die off. So when they encounter each other, they destroy each other. And what is that?
Annihilation.
So yes, when they encounter each other, they destroy each other through an annihilation reaction. Right? But that reaction, well, we can't just get rid of matter, right? We can't just get rid of mass. What happens to matter? How do we remove matter? Go back.
High energy.
Or actually, sorry, I had a new one.
This one?
Back one. How do we remove matter? Back into energy. So when these two collide, they destroy each other, completely vanish, and instead create energy. How much energy?
The same, like half. Oh, I see. Energy doesn't get destroyed, so it should be equal.
So, how much energy?
Oh, I see. Because
0.51.
But if you add another 0.511, what does that equal to?
So,
What?
0.51 plus 0.51. What do you get?
1.2. That was 1.22.
1.02.
Exactly.
So that would be another pair production.
So, the idea here is that why do we need a minimum of 1.02 mega electron volts? Because that's the minimum energy needed to create two particles. When those two particles get turned back into energy, they create that exact same amount of energy, right? So, one electron and one positron, those two combined are equal to 1.02 mega electron volts. Each one is worth 0.51 kilo electron volts. Or sorry, 0.51 mega electron volts, right? So, when they destroy each other, they create, or they give you back the same amount of energy needed to create them, right? Equivalent exchange. Energy comes in, makes matter, matter goes away, gives you back the same amount of energy. But instead of a single photon this time, they give you 2 photons. And there's something very special about these 2 photons.
Go opposite directions.
They go in exactly opposite directions. So if one is going this way, where's the other one going? That way. If one's going this way, where's the other one going?
Going down.
If one goes this way, where's the other one going? If one's going this way, right? Exactly opposite, right? Doesn't matter which way, right? They're going exactly opposite to each other.
Freestyle?
Dance moves.
That's a workout.
Yeah,
You know how they do
that's-
it? Oh,
Should have swam.
This one?
Are we gonna have to know that number exactly, because it doesn't necessarily have to be 1.02?
So this one you need to know, yes, is always going to be 0.051.
But you said that's the minimum.
0.5. So yes, the 1.02 is the minimum, that is true. But when these particles combine, they will only produce 0.51.
So it's not exact, so it won't.
So this is almost like a characteristic in that it can only produce this number. You cannot get a number higher or lower than this. It will always give you this number.
Okay, so it's not half, it's not gonna always be half.
It's, I should say it's half of the minimum. The minimum is always 1.02, this always gives you half of the minimum. It can be higher, we don't care about how much higher, this is always half of the minimum.
So, okay, so.
So your minimum is 1.02, correct? You can be above the minimum, you can be 10, it doesn't matter. The minimum is 1.02, this is always half of the minimum. This is always half of 1.02.
When they collide and it makes the two photons, it's gonna have that energy, each photon will have that energy.
So it's always gonna equal 1.02.
The
No, no,
minimum.
So this is, the two photons created at the end will always equal 0.511.
No, I'm talking about the two, they're always
Mhm.
gonna
That can be
equal.
one.
So you're talking about the electron and the positron when they are meeting each other, the energy that each of them have.
They're always gonna equal that,
Yeah, right.
even if it's higher or lower?
Yes, these two are always going to equal 0.51, right? It doesn't matter what this energy is. It can be higher than 1.02, it will always be this.
Okay.
It cannot be lower than 1.02 because you would not have produced these in the first place.
I was just, cause I put in half.
Mhm. So make sure it's half of this minimum, the at
Half
least
of the
part,
minimum, okay.
this minimum. Mhm.
And then, on the other slide, after this one, so how come whenever the positron interacts with an electron, that happens, but at the top, when the electron,
Mhm.
like it did, it's the same thing, right? Or?
Right, so the electron that's created and the positron that's created, they leave in different directions.
Okay.
So the electron goes somewhere, the positron goes somewhere, and it runs into some other different electron.
Okay.
Yes, Jay?
This is kind of off topic, but how did they discover this? Was it the
That's a-
testing for? Nukes,
That's a great question. You'd have to refer to Professor Google on that one.
Okay.
I'm sorry, I don't have the answer.
It just seems like nuclear, you know?
Mhm, it does, yes. Probably somewhere in Los Alamos or something,
I
right?
figured.
All right.
I just want to clarify. Everybody knows it's really like two interactions that's going on. So the incident photon, it comes here, it produces a positron and an electron, right? This is the negatron that leaves, and the positron that hits another electron. This is the annihilation reaction. Everybody understand that part?
Yeah.
Okay, and the annihilation reaction, that's what creates the 0.511 MeV each. Okay, I just want to clear that out. Make sure it's not
Basically, it hits another electron in the same atom.
Any atom.
any atom, because it's drifting away from where it originated. Everybody got that?
Do you see where I was going? Like, where it come from there?
As far as what?
As far as like why I thought it was like nuke related.
I get that.
Okay.
And another key factor, like I said, this is the only one that's using PET exams, alright? So PET scans, okay? So that's another test question. It's gonna say, which interaction is found in PET scans? PET production, correct?
And what does PET stand for?
Positron emission.
Positron.
Ooh.
Hey, there's that word, right?
There we go.
Positron emission tomography. So it makes sense that positron emission tomography deals with things that have positrons.
Sounds really dangerous.
Yeah.
That's
But
it.
I like a PET scan.
You did have a PET scan?
Well, no, I mean it sounds dangerous.
Oh, it sounds dangerous to,
Well,
well,
just because like how much energy it requires. So
yes, nuclear medicine, radiation therapy, those are all very high energy, high dose
I got a question.
modalities.
Does that do more good or bad?
It, oh,
I mean, like, I was wondering, like, I was
So-
like, this can be healthy.
that's right. So it is up to the doctor and the patient to decide if the risk is worth the benefit, right? Medicine is always about risk versus benefit. Even drugs, right, are risk versus benefit. Is it worth giving you this drug to do whatever, right? What are the risks? What are the benefits? Right? X-rays, risk versus benefit. Small dose of radiation, is it worth the information we get out of it? Oh, your dad had a PET scan?
He had PET scans. Well, he had a cancer, so
Mm.
radiation and radiation therapy, CTs. They're still doing CTs. I don't know.
So for radiation therapy, are they trying to annihilate things?
Yes, that's the purpose of radiation therapy. Good. All right, let's go to the final interaction here.
So, photon disintegration. This one's really easy to remember. You know the word disintegration? What does that mean? It's like disintegrating, right? Breaking away, right? So you know it's the highest energy, right? So that's how I remember it. The energy is so high that you gotta disintegrate. Just like, you know, okay. I don't know. Alright, so the required minimum is 10 MeVs. There we go, we see the MeVs again. So that's not found in diagnostic imaging. And so the interaction between photon and nucleus. So the main difference between photodisintegration and all the other ones is that this one is directly interacting with the nucleus, causing the most energy. So you can see the incident photon, it skips all the electrons and directly hits the nucleus. And so the nucleus ejects 3 particles, okay? A neutron, a proton, and an alpha particle, okay? It's a key factor. Key, highlight this, okay? This is gonna be important.
So, Rick, think about it. Inside the nucleus of an atom, what do we find in the nucleus of an atom? Protons and neutrons, right? So you have your protons and neutrons here, your electrons are outside. So if a photon comes crashing in like a billiard ball and smashes into the nucleus, things are gonna come out, right? Well, what can come out of the nucleus? Can an electron come out of the nucleus? No, there's no electrons in here, right? So what comes out? Just, right, the stuff already inside. So a proton could come out. Or what else could come out? A neutron could come out, right? So whatever's in here, that's the stuff that can come out. Now, what is an alpha particle? It is just 2 protons, 2 neutrons, right? Stuff that is already in the nucleus. So you can knock out 2 protons, 2 neutrons in a group. That's your alpha particle, right? But once again, it's stuff that was already found in the nucleus. So only stuff in the nucleus gets knocked out in photodisintegration, right? You're getting rid of your photon and you're destroying the nucleus by knocking things out of the nucleus. Does that make sense?
Yes.
So this is probably the most simple one. It's just photon comes in, whatever's in here, something comes out.
So we're showing neutrons and almost always neutron comes out, sir?
Most common. Neutrons are the most common thing to leave.
And so you said 2 protons and 2 neutrons make up that alpha particle?
So write that down, guys. An alpha particle consists of 2 neutrons and 2 protons.
Pair production, it interacts with the
Nuclear or go ahead.
With the pair production?
Yeah.
Yeah, the nuclear field. So basically, just be this space right here. You see how the space is closest to the nucleus? It's not affecting with the orbital, or it's not affecting with the nucleus. It's just this space specifically around the nucleus. That makes sense?
Wait, one more time, the alpha particle.
So alpha particle consists of 2 photons and 2 neutrons.
So it's
Protons.
Protons.
2 neutrons, 2 protons.
So is it either neutron comes out or proton comes out or
Both
alpha
of them
particle?
come out. Correct. One, the other one, or both.
When it's struck. That's what you're talking
So,
about. When it's struck, either one of those.
are we still having confusion here? If we are, it's okay. We can do another activity. Do we still have confusion? Yes, no?
Maybe so.
So, we are okay?
Yeah, I think we're
I
good.
think we're good on that.
All right.
We got the only one.
Let's go to the next one.
Oh, you good. We got two flying.
Alright, so this part is very important because this is how an X-ray image comes about. Right? Why do we have blacks and whites on our X-ray image? What do you think? Carla, why do we have blacks and whites on our X-ray image? What makes the X-ray image black? More penetration, more X-rays reaching the IR. Great. What makes the X-ray white, Samantha?
Oh, what makes it white?
Why does
It's
bone show
just-
up white?
Oh, it's the stuff that's not hitting the IR.
Great, stuff that's not hitting IR. So why do X-rays not hit the IR when they run into bone? Absorb. So differential absorption. Different types of anatomy absorb X-rays differently, right? Some anatomy lets X-rays through, right? Our radiolucent anatomy, right? Some anatomy absorbs X-rays a lot. It does not let the X-rays through, right? Our radiopaque anatomy. So, differential absorption is just the difference in how tissues absorb X-rays. And because there are differences, we can tell tissues apart. I can tell where bone is and where air is because they absorb X-rays differently. I can tell the difference between the spine and the liver because they absorb X-rays differently. I can tell the difference between the phalange and the soft tissue around the phalange because they absorb X-rays differently. Does that make sense? That concept is differential absorption, the difference in absorption. That is all we are talking about here, right? Different body parts absorb X-rays differently. Why? Why do different body parts absorb X-rays differently? Johns.
Because some of them have a different atomic number.
Yes, sir.
Great, so we come back to our atomic number, right? Bone, higher atomic number, so absorbs more. Soft tissue, lower atomic number, absorbs less, right? So radiopaque absorption, that's gonna be our bone. Radiolucent transmission, that's our air. And then soft tissue is somewhere in between.
Question. I remember you having a test. It was like which one has more absorption. It was water was an example.
Mm-hmm.
Was that considered? Does it absorb a lot or no?
It depends on what you are comparing it to.
To bone.
Right, so water would absorb less than bone.
Bone. Okay. And then tissue and water.
Soft tissue would absorb less than water.
Water. Okay. That's gonna be your test.
Right, water's kind of in the middle, right? Water, you've got bone and metal above it, but you've got soft tissue, you've got air below it.
So why would soft tissue absorb less than water?
Water has a higher atomic number than
Oh, I
soft
see.
tissue does. Also, it's more dense. Alright, so let's go to the next one.
So yeah, so transmission. This is preferably in the lungs. Whenever you take a chest X-ray, that's just telling you the photons are passing through the lungs, hitting the IR, which makes
There's
the
nothing
image
on there.
black. There's no absorption going through, right? So the X-ray photons will pass through the body, required in order to create an image, causes the area that receptor that reaches to darken. So yeah, for the lungs, when you take a chest X-ray, what is being absorbed, right? Bone. That's the white part. That's the radiopaque area. And the lungs are the radiolucent areas, which the transmission is going through. So if there's more transmission, it's just black. If it's radiopaque, it's just absorption in the short term. Everybody good on this slide?
Yep.
So absorption, same concept. So the X-ray photons, which are attenuated by the body and do not reach the image receptor. Another word that Mr. Phung can use here, he can, instead of saying absorption, he can say attenuated. So he can say what part of the body has the most attenuation. You would say bone or metal, depending, right? It's required in order to create an image, because without any of the absorption, you can't tell what the bones is, right? It'd just be all black. It was all transmission, correct? And causes the area of the image receptor they do not reach to remain light. So yeah, so the reason why it's white is because those X-rays that hit in the bone, they're all being absorbed there. There's no way of transmission to hit the IR. That's why it's showing up white on the IR. Everybody understand that concept?
Yes.
Yep. Okay.
So just one quick question then. Are absorption and attenuation exactly the same thing? No?
I thought yes.
I
Yes.
thought yes.
Alright, so, right, Mansi, go ahead.
Isn't attenuation anything that is not transmission?
Well, what else would there be aside from absorption?
Scatter.
Scatter, yes. Attenuation is both absorption and scatter. Anything that reduces the number of X-rays being transmitted is attenuation. So absorption and scatter are both attenuation. So just be careful. The words are very similar. They can often be used in the same scenarios, but there are differences that you need to watch out for.
So you can't use the absorption and attenuation interchangeably, right? Because they don't mean exactly the same thing.
Not all the time. So with Mr. Gamboa's example, with bone, yes, we could use absorption or we could use attenuation, right? Bone has high absorption, bone has high attenuation. But if the question instead was something like, let's say, if, well, I can't think of an example right now, but if it was something about only absorption, right? And one of the answers involves scatter, right? Then you can't use absorption and attenuation interchangeably in that case. Speaking of scatter, I think the next slide is. Nope. Nope. I tricked myself. All right, so just real quick about scatter. Notice scatter was not something used to create the image, right? We need absorption, we need transmission, but scatter does not help produce our image. Transmission makes the image dark, absorption makes the image white, so we can tell the difference between them. Scatter does not do either of them. Scatter does not do that, right? Scatter does not depend on the anatomy. Scatter just exists. And so it just makes the whole image exposed. It doesn't tell you the differences between anatomy, and so there is no benefit to having scatter. Fog. All right, so final section of the chapter. This part is important. This is your introduction to radiobiology.
What?
So,
What are we
Next
doing
semester, right?
now?
Sounds like fun.
So make sure you pay attention here.
so yeah, so molecular level interaction. So this is basically the effects that what you call it, radiation can have on the DNA. So this is, if you guys haven't seen it, this is a double helix. Another name is the DNA, correct? And so within these DNAs, we have different types of code. Well, that's different. I was about to say A, B, C, but that's different. So basically, so 3 interactions can cause from this radiation, right? So this is the main 3 chemical reactions. So we have main chain scission, cross-linking, and point lesion. Okay. So highlight these. These are the main 3 effects that can happen.
Now, before Mr. Gamboa goes any further, I just want us to look at these names. Right, remember, I said names in radiology usually make sense. So let's see if we can figure out what these could possibly mean without even looking at information. Main chain scission. What does scission sound like?
Scissor.
Cutting off.
Scissors. Cutting. So what do you think happens?
It's cutting off.
Right.
off the main chain.
It gets cut. All right, great. Cross-linking. What does that sound like?
We're crossing each other.
Linking together.
All right, linking together. Right. So going across and linking together. Great. And then point lesion. Point.
Like a point, maybe it's
It's
going
like
to the point
injury.
of the chain.
So what is a point?
Could be
Point
just
of
A dot,
A dot.
maybe a connected dot.
A dot, right? Just a single point, right? Point. Just a single location. Right? So keep that in mind. Let's go on.
Okay, so for example, like he said, main chain scission. So you can see these blue lines that are hitting the DNA. So the blue is representing the X-ray, and the yellow is representing the DNA. So main chain scission, we already agreed that it's cutting, right? So you can see how it's sliced. You can probably see on the TVs a little bit better, but you can see how the X-rays are slicing the DNA. Okay? And then cross-linking, right? Connecting, right? So as you can see, the X-rays are hitting, and it's connecting these 2, right? Boom, and that's a whole different code right there. Got another cross-linking. And then point lesion, it's just represented as a point.
Like connecting the dot.
So making a single change at that one point.
1 point.
It's like a wound.
Yeah.
Kind of like a wound.
Or at the top of that little curve.
It can be any point.
Okay.
It can be down here.
Could be anywhere on here.
It's just a specific spot on the DNA chain.
Did you say making a
Right.
change, sir?
Yeah, so the X-ray hits it, and maybe it just turns the A into a G, right? Or it turns the code from a T into a C, right? Just makes a change, right, to that one particular point.
And this can be really dramatic because let's say codes is really weird. So let's say there's a code, the point lesion affects the code, and then all of a sudden you have a disformity or a future disformity that can lead up to your kid. That's just how dangerous this can be. So, okay, so
Sorry, yes, Charles.
Just to recap,
Mhm.
from my brain,
Yes.
main change vision, the x-rays cut through the DNA.
yes,
Mhm.
In cross-linking, the x-rays link DNA.
Correct. They connect points that should not be
should not
connected.
be together.
And then in point lesions, a single change can happen at any one point in the DNA.
Yeah.
Correct.
Okay.
So yeah, for example, say it's an A, the X-ray hits it and it turns that letter of code to a T. You know,
Mhm.
that's what point lesion is.
Right.
Can you repeat cross-link? You said it connects,
Two locations which should not be connected.
Mhm.
So using point lesion as an example, just to give an example of why this is important, right? It looks really small compared to the rest of them, correct? But let's say that, right, DNA is instructions. So let's say that you are reading some instructions word for word, right? And you would do exactly what those instructions said, right? And so let's say you're baking a cake, right? And it's like, all right, take butter and melt it in the microwave, right? But then this came in, made a typo, and the A in the and became an E. Take butter and. All right, guess I'll stop here. Do you see the issue here? Right? Small change, single change, but you can change the instructions entirely, right? Not going to read the rest of the sentence then. So, N. All right, N.
And that's it. Okay.
Yes.
So basically, this is the actual damage that radiation does to the insides, the tissues. and
Correct.
everything. Okay.
Like
Yeah.
Melanie?
yeah, me too.
she said, she had confusion with their analogy.
Oh, with my analogy?
Yeah. So
Oh.
it's like
Okay.
I thought I understood it, but then you said that it's just weird.
it's just like let's say you have a whole list, right? Of preparation, right? One to 10, and then the 5 just gets switched out with a 10. So you're doing the whole steps incorrectly, correct? So that's basically what he's trying to explain.
Yes, John.
Is there a more common one that occurs, or is it?
More common, any of them can occur. Multiple of them can occur. So,
Save me some.
if I would assume that point lesion is probably going to be the most common. I think the least effort to cause a point lesion.
And it's not guaranteed that one of the three will happen. There's a chance.
Correct. It's a chance that one of the three will happen. It's not guaranteed. And just because something happens doesn't guarantee that damage will be done. The body is very good at repairing itself. So just because there's major incision doesn't mean the body can't come back and connect them again.
Oh.
Now, will the body connect it correctly? Once again, I can't guarantee that. Right? Lots of different things can happen, but that's for a later course.
Is this like the effects on like Chernobyl on people how they're not extra codes and stuff like that?
Yeah,
Technically, because that's coding.
all comes down to DNA.
So yeah, coding can lead to like there's so in family trees there's coding that are more acceptable to diabetes, correct? And other families aren't. It's just depending on the genetic code. So that's why. Yeah, and then this is out of the topic, but in the future there's like coding where they take that genetic code out and then your family won't be acceptable to diabetes. So for that example, so yeah. So micro level interactions can change the genes and DNA, like I just said. You know, they can take it out a family tree if they wanted to. It can cause rupture of cell membrane. It can cause radiolysis of water. So, yeah, go ahead.
So, radiolysis. Let's break that word down. Radio, what do you think radio means? Radiation, great. What's lysis?
Breaking, splitting.
Lysis, death, breaking, splitting. So, the death through radiation of
Water.
water. So if we break up water, what is water?
H2O.
H2O, great. If we break up water, what do we get?
Hydrogen and oxygen.
We got one hydrogen, and what's the other part?
Two
H2O.
Well, it's H2O, right? So we've got
Two
two H's and one O.
Yeah.
So if we cut it, right? We've got an H and we've got an
Oh.
Two O's.
H.
O.
Square.
What's connected to the O still?
H.
The second H, right? So we've got an H, we've got
Hydroxides.
OH.
Yeah,
Right? H and we've got OH. Now, let's say you have two OHs and they combine together. What is H2O2? Any ideas?
Oh, hydrogen peroxide.
Hydrogen peroxide. Great. Where do you see hydrogen peroxide?
And cleaning.
At the house.
At the house? Drugstores, right? Why do drugstores sell hydrogen peroxide?
To clean, disinfect.
Clean, disinfectant, right? So, what does hydrogen peroxide do to cells?
Kills
It
them.
helps it, like cleans it out, right?
Right, it kills things, right? It kills germs, right?
Yeah.
Now imagine producing hydrogen peroxide inside your cells.
You're dead.
Dangerous, right? So radiolysis of water. Radiation can destroy water in the cells, and when the water gets destroyed, it can reform into hydrogen peroxide in the cell. So we see how radiation can be dangerous in more ways than just affecting DNA, right? And that is why your cells have these organelles called peroxisomes to digest hydrogen peroxide.
What was that definition you said, the death through?
Or the destruction
Yeah.
through radiation of water.
Oh, okay.
Radiation destroys water, radiolysis. Will you need to know this?
No.
Not yet.
Not yet.
Not yet. Jalen's the one that needs to worry about it next semester.
You better pay attention now too.
You better pay attention now.
And later.
But I think that's it, right?
That's the last one.
That's what you
So
saw.
review. We got another pop quiz, guys. So put up.
Okay, so first of all, how do we feel?
Not good.
That was a little better.
See, that one's easier than
Yeah.
the other two, right?
Yeah.
The only one that was hard for you was what?
It was all of it.
Compton,
Photoelectric
Photoelectric.
absorption. Photoelectric absorption is the only one that's difficult for you guys, in my opinion. I feel like you guys know what Compton is. You guys know what classical is.
You have faith in us.
All right, so let's talk.